Good morning, everyone. We are going to do a bit of review on image acquisition and evaluation and review the things that we learned in exposure class. So, even though so many things, some technical parts of our occupation have changed over the years, we still have to look at certain things. We have to look at the body habitus. Are we looking at muscle? Are we looking at fluff? And we're looking at pathologies, all of that. We still have to be aware of those processes, and we still have to position correctly. But we're going to look at technical factors and image quality. So looking at geometric factors, what is that? That is detail, and other words for detail, resolution, spatial resolution. And we also know that there's a term distortion specifically for elongation and foreshortening, which is shape distortion, and magnification, which is size distortion. The factors that contribute to detail or resolution are distance, patience factors, such as where in the patient's body is the part that we're looking at. Is it going to be magnified because it is so far away from the image receptor? And focal spot size affects detail as well. And Carlton and Adler are really good about making these concept maps. When you're looking at recorded detail, there are three factors: the geometry of the beam, the image receptor itself, and motion. And we all know that motion is the greatest enemy of recorded detail. What is involved in the geometry of the beam? Well, it's the focal spot and distances, and within the distances you have OID and SID. Image receptors, do we have a digital system? Is it still film screen? I know not many facilities have that around the Seattle area. However, there are parts of the world that are still using film screen. And then motion. Is the problem with motion, is it voluntary? Did we instruct our patients correctly? Involuntary. Let's say a patient has a tremor. They're not able to hold still. And then sometimes we actually move the equipment and use it to our advantage. So this little concept map, I think, helps give you a good overall view of what goes into recorded detail. And I want you to think about, what do we use to assess recorded detail? And in the old days, we used a device like this. We would take an x-ray at a certain distance, and the unit of resolution is line pairs per millimeter, as you can see here. And depending on whether you can see the lines, you will get an idea how many line pairs per millimeter you're going to see on your image. We see that we really can't differentiate the lines here, and 5 line pairs per millimeter is a really good resolution level. Usually we're somewhere around 3, 2.5. Now, if we don't have that test tool, we look at trabecular pattern of the bones. How sharply can we differentiate the trabeculation? So, 3 geometric factors that affect recorded detail: magnification, distortion, and focal spot blur. And we'll get into all of those in the course of this lecture. So, if we're looking at magnification, there is a mathematical formula to help us figure out the magnification factor. What is that? That is basically a number that we can multiply the size of the object by and get the actual image size, or divide the image size by the object size and you get your magnification factor. So the example given is if a heart measures 2.5 centimeters at its maximum width and its image measures 14.7, what is the magnification factor? And to help us with this, I am going to try out a new tool called Whiteboard. And let me line this up and let's take a look at that problem. Okay, if you remember, the image size was given as 14.7. The object itself, the heart, was 12.5. And that's in centimeters. And if you remember our friend the triangle, we know that the magnification factor equals the image size over the object size. And if you remember that saying from an old student, mofo, I'm out. So basically, to figure out the magnification factor, we need to take the image size and divide it by the object size, and then we would get the magnification factor, which in this case is 1.17. By the way, for most radiographic images, the magnification factor is about 1.1. So we see that in this problem, it came out to be very close to what the average magnification factor is. Remember the factors affecting distortion are object thickness, object position, and object shape. And what that means to us is how thick is the patient, where in the body does the object that we're trying to see reside, and is the patient rotated to give that object a different shape. So if the object plane and the image plane are not parallel, you get distortion. All right, this slide is talking about recorded detail and how we assess it without the tools to find out the line pairs per millimeter. And as we talked about before, we look at the trabecular pattern in the bones to see what kind of sharpness we're seeing in our image. And if you remember the terms penumbra and umbra, penumbra is that blurry edge, and umbra is the actual shadow of the part. Now, these two images have differing recorded detail. The one here on your left is a nice X-ray of a young person's wrist, and we're seeing good trabecular pattern here. And so this has good sharpness of detail. This knee, however, we're seeing some good trabecular pattern down here, but not so much up here. And in fact, if you think about what projection this is, the tunnel view of the knee, you remember that the femur or the leg is flexed. And so you're going through a greater thickness of the femur up here, so we're not actually getting full penetration, and therefore we're not able to see the detail as well as we might otherwise. So the image on your right is showing fair resolution on the tib fib, but not so great on the femur. Now, what about spatial resolution? Remember, that's another term for detail. One of the factors in being able to see detail is noise. So one of the causes of noise is quantum model. And if you remember, the definition of quantum model could be photon starvation. There just weren't enough photons to give us a good exposure of the part we're looking at, so we can't see the detail. You see on this bottom image, it looks like they've increased their MAS, and now we are seeing much more detail. Up here, it's very spotty looking, and that is considered noise. And if you remember, noise can be measured by the signal-to-noise ratio in digital imaging. Basically, that is the signal or the information that you want in your image versus the amount of noise, the background noise in the image. And so you want a high signal-to-noise ratio. You want more signal than there is noise. As you can see here on the right, there is a lot more noise than there is signal, and so you get a very grayed out image, unable to actually see the detail. And this is called a power ratio between the signal, which is useful information, and the noise, which is background information. So it would be the signal over the noise, as you see here, the signal to noise ratio. So components of noise, film graininess. Now you won't need to know about that because the registry is not going to test you on film screen. However, a structure model, that would be pathology or something within the patient that is causing model. Quantum model is when there aren't enough photons to give us a good exposure. And then scatter radiation is another factor in noise on your image. Too much scatter is going to give you a very grayed out image. Again, the things that contribute to image noise: quantum model, which is insufficient exposure to the IR, and that is under our control because we can control how much MAS we choose to make the exposure with. And then scatter is useless information. We cannot use it to diagnose. We have some control over that. We can try and control its production by collimating our images and using grids that help clean up the scatter once it is produced. And I found these images. It's the same patient with the exact same condition here, and this image has a lot more scatter in the background, and it's looking very gray. It's hiding, that gray fog is hiding the detail in this bowel here. Once you clean up some of that scatter, I'm guessing this image was done without a grid and this one was done with a grid. The one with the grid allows us to see the detail a lot better. Okay, another effect on a recorded detail would be the focal spot size. And we know that we have small focal spot versus large focal spot. We use small focal spot for smaller body parts. And we also know that because of the level of heat created with higher techniques, we need a larger focal spot in order to contain all of the heat created from that large technique that we use. The focal spot is actually rectangular in shape, the actual focal spot inside the tube. And you can see it here. And they're giving you an idea of, remember we talked about penumbra and umbra. So the penumbra is this dark area here, which would represent an area of blurring at the edge of the image. of the object. And here with the larger focal spot, we see that the penumbra is larger. So let me actually show you demonstrate a little something about the focal spot size. And let me get the white. Okay, so I have drawn a rectangle, and let's assume that is the actual focal spot in the X-ray tube. But we need to remember this is looking at it straight on, and the anode, you remember, is angled. And this rectangle is right here. Now imagine yourself being the patient, and you are looking straight up at this. And what you're going to see as you're looking up, because that's angled, you're going to see a square. Okay? And that's because of that angle of the anode. And since we're talking about the penumbra, there is a formula for figuring out the size of the penumbra. I can almost guarantee you that this formula will not be on the registry. But just know that, or recognize that they're taking into account the focal spot size, that's the FSS, and the OID, and then the SOD, which is going to tell you the width of that penumbra, that blurred edge of your object in the image. Now, I mentioned actual focal spot. This is just reminding you that the actual focal spot is inside the X-ray tube. The effective focal spot is that which is projected down onto the patient. So the effective focal spot is foreshortened, and it's going to appear as a square. And that brings us to the line focus principle, which states that the effective focal spot, which is down here, will be smaller than the actual focal spot, which is up here, as long as the target angle, okay, this angle here, is less than 45 degrees. Know that the effective focal spot size is controlled by the size of the actual focal spot and the anode target angle. And we know that the smaller the target angle, the smaller the effective focal spot. Now what this slide is illustrating is that you have the same size electron beam coming from the cathode on both of these, but it is the angle of the anode that determines the size of that effective focal spot. And so with the larger angle, this one has a 24-degree angle, you have a larger effective focal spot. Therefore, you're going to have more penumbra. And on that smaller anode angle, you get a smaller effective focal spot and less of a penumbra. And this image is from your book. It's hard to include all three on the same slide without making it so small, but they're showing you what the penumbra looks like based on the focal spot size here, the difference in the penumbra between small and large focal spots, the effect that OID has on the penumbra, which you can see the smaller the OID, the less the penumbra. Larger the OID, the greater the penumbra. And then here is the demonstration of what happens with SID. When you have a longer SID, you have less penumbra. A shorter SID gives you a greater penumbra. And that penumbra represents the blur caused by the line focus principle. Now, there is a side effect to the line focus principle, and that is the anode heel effect. Because we want a sharp angle on that anode to have a smaller effective focal spot, we end up with a portion of the anode, the heel part right here, absorbing some of the photons that are created. And that means that there's a variation in the number of photons that make it out of the tube at the anode side compared to the cathode side, which allows more photons to actually exit the tube because they don't have to travel through the anode. And there's about a 45% difference between the cathode and anode end. And here we can see the percentages. If you assume that the central ray is 100% of the intensity of the beam, on the anode side, here's the heel here, there are fewer photons that make it through, as opposed to on the cathode side, you have more photons than you would even in the central ray. You notice the anode heel effect most with small focal spots, and if you're using a large film size, and if you're using a short SID, the anode heel effect is much more obvious. Now, yes, we do use that to our advantage. If we're doing a body part that varies in thickness from one end to the other, we can put the thicker end at the cathode side, and there would be more photons to penetrate that part, as opposed to the thinner side, which there are fewer photons, and we're not going to burn out the image of the anatomy on that end. Remember, motion is the greatest enemy of detail, and there are various types of motion. Voluntary motion is best controlled by communication with the patient. I believe that is a review question I've seen in a number of different sites. Involuntary motion, the only way we can control that is immobilization, sponges, tape, and making our exposure time as small as possible. And these next slides are basically saying the same thing that I just said. Peristaltic activity is involuntary, muscle spasms. The beating of the heart is involuntary. All right, sometimes we use deliberate motion. Here they're showing you tomograms, and that is where both the tube and the image receptor move during the exposure. And basically that creates a fulcrum, or a plane, in which the only details that can be seen are in that fulcrum or plane. The rest above and below is blurred out. And this is what we used to examine parts better before we had CT. Okay, now that we've discussed detail, I want to get into the exposure of the IR, and that begins back in the tube with our MA, which when we set our MA, it determines the quantity of photons in the beam, and another word for that is intensity. So I want you to think about when you change your MA station on your equipment, what happens within the machine? What happens when you change your MA station? It changes the current to the filament. So now you have more electrons moving through that thin wire in the filament. What happens then? So your mind should go to more electrons boil off in thermionic emission. All right, if we have more electrons available at the cathode, what happens with X-ray production. It increases. So milliamperage is, how is it related to the tube current? And it is directly related to the tube current. The milliamperage, when you increase your milliamperage, you increase the tube current, the number of electrons that flow across from cathode to anode, and vice versa. So if the milliamperage is doubled, so are the number of electrons that are able to cross the tube. So let's look back at some terminology to do with current. The unit of current is the ampere, and the definition of ampere is 1 amp is equal to 1 coulomb of electric charge flowing in 1 second within a conductor. And that means, what is a coulomb? If you remember, a coulomb is 6.3 times 10 to the 18th electrons. And a coulomb is a measurement of a bunch of electrons, a bunch of charges. And if you're talking about current, those charges are moving. So you would say 1 ampere is equal to 1 coulomb per second. 1 coulomb is 6.3 times 10 to the 18th electrons per second. And 1 milliamp is 6.3 times 10 to the 15th electrons per second. And there's a little problem down here asking you, if you choose the 1000 mA station, how many electrons will flow from cathode to anode. And you have to remember that 1000 milliamperes is equal to 1 amp. Therefore, there would be 6.3 times 10 to the 18th electrons flowing through the tube per second. All right, so tube current has a direct relationship to the beam intensity. Changing from 200 mA to 300 mA will give you a 50% increase in the number of electrons that boil off, and that gives you a 50% increase in the number of photons created. Now, we all know exposure time controls the length of the exposure. It is directly proportional to the intensity of the beam, and we usually use shorter exposure times to reduce motion artifacts. All right, MAS, MA times seconds equals MAS. Remember that MAS controls the quantity of photons created. Therefore, it's going to control the patient dose that is received from the exposure, and that is going to determine the density or brightness of the image. And in other words, the image receptor exposure. All right, with MAS comes the reciprocity law. You should know the definition for that. I would guess that there'd be a question about it on the registry. So what does it mean? You will get the same density or image receptor exposure even if you use different combinations of MA and time, as long as your total MAS is the same. And here I am giving you some examples. 50 MA and 0.22 seconds gives us 10 MAS. You can change the 100 to 100 MA times 0.1 seconds, and you still have 10 MAS. 200 MA times 0.05 seconds is still 10 MAS. And that is all that the reciprocity law means. All right, now differentiating between the terms density and brightness. We use density in film screen imaging because it indicated the amount of silver that was deposited on the hard copy film. Brightness we use to express how dark the image is in digital imaging because it is projected on a monitor, and we can control that brightness on the monitor itself. And so high brightness would be a really light image. Low brightness would be a dark image. Now, this slide is talking about the reciprocity law in film screen imaging. We see here they used 3.2 MAS on these first two images, but they used different MA and time settings. As long as it equals 3.2 MAS, you're going to get the same density on your image. Here, they did not reduce the time when they doubled their MA, and so they ended up with 6.4 MAS, and you can see it's much darker than the other two images. Now, we know that in digital imaging, our choice of MAS is important, but we have wide latitude when it comes to technique choice in digital imaging, because the computer will self-correct that image, and we'll get into the details of that in a little bit. I don't know how much you remember from exposure class, but we know that we can play with the images after we have them on the monitor, and we call that post-processing, but that has its limitations. If you have horribly overexposed an image, there's not much correction that can be done with it. There is a point after which your image is going to look very grayed out. It's too dark, and the radiologist is not going to be able to adjust that so that they can see what they need. All right, this slide is an example of very different techniques being used on digital imaging, and what happens is the computer corrects the image to look like what is in the lookup table, and it's going to adjust the density and contrast to look as much like that perfect image that's in the lookup table as possible. And so these four images all look diagnostic. They look like we could turn them in, but if you look at the exposure numbers, 2099 S number means really underexposed. With the S numbers, the lower the number, the greater exposure. So here we have a 29S number, so that was grossly overexposed. 50 MAS on a skull, that's way too much. And yet it looks quite similar to the one that we used 12 MAS on. The only difference is your S number. Okay, KVP, remember that is the quality. It's how energetic are those photons, their energy, and therefore the penetrability of those photons. Now, the KVP, we know, influences the amount of scatter produced. A low KVP is going to give you less scatter than a high KVP. And you remember the mnemonic, the more K, the more gray. So the more KVP you have, the more shades of gray you're going to have in your image because of scatter. And therefore, that has a huge effect on contrast. Now, if you remember, KVP can also influence the quantity of photons in the beam. And that is because a higher KVP will drive more electrons across the tube at a faster speed, and therefore create more photons at the target. And therefore, KVP has some effect on quantity. It isn't as reliable that we can every day use a formula to figure out changes in KVP and figuring out the quantity of photons. This formula is in your Carlton and Adler book. We don't use it because it's not that reliable to use it to change our techniques. All right, so how will changing the KVP affect quality and quantity? So you want to know that increasing KVP increases beam penetrability, the quality, and the quantity. Decreasing KVP will decrease the penetrability and decrease the quantity. And since we're talking about KVP, we should talk about the 15% rule. Now, this applies mostly to film screen. It was predictable. If you wanted to double the density on a film screen image, you could increase your KVP by 15%. Now, that's if you want to double the density. If you want to have a longer scale of contrast, but you want to keep the same density, then you would increase your KVP by 15%, but compensate for that by cutting the mass in half. So let's take this example. An X-ray image was made using 400 MA, 25 milliseconds, and 84 KVP. In order to double the density without adjusting MAS, what new KVP should be used? So don't start by figuring out your MAS. We're not looking at that. So there are some distractors in this problem. They just want you to change the KVP. We want to double the density. So we are at 84 KVP. 15% of 84 is 12.6. You add that to the 84 and you get 97. So you would set your KVP at 97 instead of 84, and you would double the density on your image. All right, and this slide is an example of what happens with, you have an exposure here, 70 KVP at 1 MAS. What they did was they changed their KVP. They lowered KVP by 15%, but kept the mass the same. And what happened? You end up with a light image, half the density. So you have to use that 15% rule. If you decrease your KVP by 15%, you need to double your MAS. So they went up to 2 MAS. Now we have a much better image here. Okay, for review, what affects X-ray intensity? Remember, intensity is another term for how many photons in the beam. So, the quantitative factors are MAS. We talked about KVP. KVP can have an effect on the number of photons in the beam. Distance is going to affect the X-ray intensity that reaches the IR. And as is filtration. If you remember, filtration is going to absorb the lower energy photons in the beam. And those photons would have merely been a dose to the patient's skin. They wouldn't have made it through the patient anyway. So that reduces patient dose and therefore reduces the number of photons that reach the IR. Now, the qualitative factors are going to be KVP and filtration. Now, how is it that filtration is going to change the intensity of the beam? Well, if you look at Okay, so let's take a look at the emission spectrum. If we have the KeV on the x-axis and the number of photons on the y-axis, our emission spectrum is going to look like this, or I'm sure it looks much better in the book. Anyway, so what we have is we've graphed the number of photons created with each KeV level. So with each increase in KeV, you are getting a different number of photons created with that energy. Now, here's what happens with filtration. These photons created at this end of the spectrum are weak, and they're not going to make it through the patient. They're going to be absorbed in the skin. So if we can filter those out, if we can absorb those before they reach the patient, we are reducing the total number of photons in the beam. However, because we're getting rid of these lower energy photons, the average energy of the photons in the beam is going to be higher. So that is going to affect the quality of the beam. Okay, so what does distance do to the intensity of the beam? We know that the farther you are from the source of radiation, the fewer photons are going to reach the IR at that distance because of divergence of the beam. So the primary or useful beam is the photons that actually exit the tube. All right, so at this level, more of the photons are going to strike the IR than if we were at this distance from the source of radiation. And this drawing should look very familiar to you, and the first thing you should think is inverse square law. And remember, inverse square law is used when talking about dose. The inverse square law looks like this, I1 over I2, and the I stands for intensity, equals D2 over D1. And I want you to notice that the primary factors and then the secondary factors are inverse. So this is the inverse square law. This is what you use when you're trying to figure out what the dose is going to be if you change your distance. But what we've derived from that inverse square law is the density maintenance formula, or direct square law. This is accurate enough to allow us to change our MAS if we have to change the distance. So to recognize the difference between looking for a change in dose when you change distance, you would look for Rankine or milliRankine or some dose factor in your original intensity and your second intensity. If it's the density maintenance formula, you're going to see in the problem the term maintain the same IR exposure, maintain the same density, maintain the same brightness. And you would use the direct square law. MAS1 over MAS2 equals D1 over D2. And don't forget to square it. So notice that your primary factors are both on top, and the secondary factors are both on the bottom. So I don't know if that'll help you recognize when to use which formula, but hopefully it will. And here we have an example showing you you're using the same KVP, but they have changed the distance. So going from 36 to 72, they didn't change their MAS and they ended up with a lighter image. You have to change the MAS to compensate for that increase in distance because fewer photons will reach the IR. And here we see going from 36 to 72, you need to quadruple your original technique. All right, so let's take a look at a problem using the direct square law. Our original SID is 40 inches, and we're using 50 MAS for this problem. And our new SID is going to be 44, and they want to know what MAS do you use in order to compensate for the change in distance. Okay, so we're starting at 40 inches, going to 44 inches, and our original MAS is 50. So our MAS 1 is 50. MAS 2, we don't know, so we call that X. Our original distance is 40, and we're going to put that right alongside the original technique. And our new distance is 44. And then don't forget to square it. Okay, from here, order of operations, you have to bring that square in. So 40 squared is 1600. 44 squared is 1936. And the 50 over X stays the same. So what do we do next? So 1600x equals 50 times 1936, which is 96,800. And to isolate the x, we divide by 1600. Divide both sides so they don't feel bad. And 96,800 divided by 1600 is 60.5. So here is another example of using the direct square law to change your MAS if you're changing your distance. I'm not going to go through that again. I would suggest you try it on your own. I also suggest that before you submit the answer, go back and double check. Let's go back to this other one. And on this one, we ended up with 60.5 MAS. Take a look, go back and take a look, and we increased our distance. Therefore, fewer photons are going to reach the IR. So if we got a number that's greater than 50, what we started with, then we did it correctly. Okay, so always go back and see if it logically makes sense. If the answer you get logically makes sense. So what I'm going to do from here, I'm sure you're tired of hearing my voice. I'm going to assign you in pairs to create some brief PowerPoint presentations on the topics that come up next in this video. And it's in your prep book, chapter 11. I am going to outline your assigned topics on Blackboard. You will see a group setting come up, and you'll see who you've been assigned to work with. And then I would like you guys to work together and create a brief PowerPoint on the topic that I assign. And then we're going to upload those PowerPoints to Blackboard so that everyone can see them. And that will constitute your attendance at class today.